what we're going to do is we're going to look at the graphs that you guys have submitted, and we're going to come up with some relationships, and then we're going to basically come up with the formulas for this unit. You're going to sit back and enjoy the spectacle of the Circular Motion Lab summary, Nate. You can write these down if you want. Of course, I'll post these to Schoology right after I'm done. You do what you need to do. I will explain what's going on. You do what you need to do. Okay, so what we're going to do is we're going to take the results of our experiment and derive some formulas that relate centripetal force Fc to the various aspects of UCM. So the first part of the lab, we changed the number of washers, right? And so what did you get, what kind of relationship, Billy was talking about, what kind of relationship is there between the number of washers and the speed? The more washers, the faster it goes, or the slower it goes? Faster it goes. And we had to do some sort of fancy sort of stuff. Well, I had you go 1 over FC, and we did period squared, but regardless, you should have gotten, hello? Oh, I haven't shared it, have I? Sorry. Thank you. You should have got, now, where's my graph? There it is right there. Come on. Show me that graph. Come on. What the heck? There it is. Is that what you got? Yes? Josh, you were a grapher. Carla, you were a grapher, right? Did you get that kind of graph? You don't remember? Okay. So what this tells us is that it was not a linear relationship. Okay? This suggests that it may be an inverse or an inverse squared relationship. So a real scientist, to try to figure it out, I mean, they would use a computer, but in the old days, they would have graphed t squared versus 1 over fc, which is what I had you do. And when you did that, you should have got a linear one. Did you get that, Josh, in the second one? Yes. Or linear-ish, right? So this suggests that, where is it? Come on. I never know if I have to write it or not. Thought I had it all set up. I don't see it. So this suggests then, oh no, maybe it's right there. I see it now. It's right there. It was so small I could barely see it. This tells us then that the period squared is proportional to 1 over fc, because this was our 1 over fc here, and this was period squared. And so when you get a linear relationship like that, or when you get it like this, right, it tells us that it's inverse. And then when we graph it like that and we get that straight line, this suggests then that t squared is proportional to 1 over fc. In other words, the bigger the number of washers, the faster it goes, and the faster it goes, that means the smaller the period is. Right? Pardon me? No, that's proportional to, right? Proportional to. So what you got out of the first part of the lab is that t squared is proportional to 1 over fc. That's what you should have discovered. I have to sort of, help you along to make that discovery. But Billy actually did make it in some sense. He said the more washers you put on, the faster it goes, right? That's what he said. Didn't hear him say it today, but he said it yesterday. Okay? Can I go on? So when you graphed period squared versus radius, when you change the length of that string, what did you get? The longer the radius, did it go slower or did it go faster? Slower. I think that's intuitive, right? And if it goes slower, then that means that the period is bigger or smaller, Cole? Bigger. Slower means that it takes longer to go around, right? And so you should have got, where is it? I'm going to play this game all day. Oh, it's right here. There, I see it. I see it. No, it's hidden. There it is. It's not small. It's just hidden. Yeah. So you should have got a linear one, and this implies that this is period squared versus radius. So we've got t squared here, we've got our radius here. So this tells us, because it's linear, then that t squared is proportional to r. The bigger the radius, the slower it goes, which increases the period, and it's period squared. Okay, so far we've got two relationships. We've got the t squared is proportional to 1 over fc, and we've also got the t squared is proportional to r. We're going to combine all these proportionality relationships together into a formula. Again, you're not responsible for recreating this derivation. I would be absolute insane to expect kids to do this. I'm just showing you where the formulas come from. It's one of the things we're supposed to do. Okay, the third relationship is based on period squared and mass. What happened when we had more rubber stoppers on the string? Did it go slower or faster? Slower, right? Which tells us then that the bigger the mass, if it goes slower, the bigger the mass, the bigger the period, or the smaller the period? Bigger the period, which should give us a, let me see if I can find it. I see it there. Oh, I know why, because I got this in my hand. That's why. Gives us a linear relationship, which implies then that t squared is proportional to m. So we've got three proportionality statements, all based on t squared. Right? The bigger the mass, the slower it goes, which means the bigger the period. The period is the time it takes to go around all at once. Okay. Yeah, but he doesn't have that intuitive sort of sense of the spinning and how fast things were going and stuff like that, right? So okay. So now what I'm going to do is I'm going to take those three proportionality statements and I'm going to combine them together. Okay. So we get, by combining our proportionalities together, we get t squared is proportional to rm over fc. Because we knew that it was proportional to r, we knew that it was proportional to m, and we knew that it was proportional to 1 over fc. I combined them together into one mega proportionality statement. Scientists generally want to have that as an equation. In the old days, I used to talk a little bit more about this. This is the first time I think you've seen it. To turn the proportionality statement into an equation, you change the proportionality symbol to equals, but to make it work, you need some number that makes it work. For example, you know that circumference is proportional to the diameter of a circle. The bigger the diameter of the circle, the bigger the circumference. To change it into an equation, we do that, but I need a proportionality constant. What is the constant that goes in there? Exactly. C is proportional, or C equals pi times D. Pi is the proportionality constant. Yes, Pat, give him a pat on the back there, Cole. Yeah, well done, Mitch. Pi is the proportionality constant that makes that work. We don't know our value of pi just yet. We don't know what it's going to be. So we're going to replace it with a generic constant, and we're going to use the letter K. Yeah, no, but we're going to need some other number, right? We're going to need some other number. So we're going to say that t squared is equal to small k rm over fc. Why isn't a c? C is a special constant of proportionality. It's the speed of light. And it's so special, it takes the letter C, 3.0 times 10 to the 8 meters per second. Nerd. That's the speed of light. I'm just making it okay to be a nerd. Sorry? I don't know why it's C. I think it's just because it's the constant. It's like the number one constant, right? So, yeah. Okay, so we're going to take that and we're going to rearrange it to, and I can't explain why, we're going to rearrange it to Fc equals, because we're most interested in how much centripetal force is. Fc is equal to Krm over t squared. So all I did here was take the t squared and the Fc and switch places. So this is my formula that our lab suggests we should get. Okay? Do we have a way to come up with the value K? What do you think? Like, I mean, we counted massive stoppers. We counted as in 1, 2, 3, 4, how many stoppers there were, because all we really cared about is what type of relationship is it. So we would have to weigh the stoppers. We would have had to have a much better value for our period. Our radius would have been had to measured, and we would have had to keep it accurate as well. And we would have had to weigh the washers, find out their centripetal force and newtons per kilogram. This seems like a lot of work, right? To come up with some K value. Is there some other mathematical way we can do it? And the answer is, you betcha. That's what we're going to do in the next slide. I sort of got ahead of myself there. Okay, so FC is equal to KRM over T squared. We're going to compare this to FC is equal to MA. F equals MA. You learn it in grade, I don't know, 8 or something, right? If I put the letter C in there, it tells me that centripetal force is equal to mass times centripetal acceleration. So I'm just going to compare the two side by side here. And what do you notice? Well, really, here we've got an M, here we've got an M. So what do you think the value for AC is? KR over T squared, exactly. AC is equal to KR over T squared. This is our predicted formula for centripetal acceleration. So we're going to attempt to derive a formula to see if it matches our prediction and to determine the value for K. So mathematically, we're going to come up with a value for K. It's going to deal with circles and geometry and all that really exciting good stuff. Are you with me so far? Are you? Let me just summarize what we've done, Nate. Is that right? What I've done is I've taken the results from the experiment, the graphs, come up with what type of relationship it is, combine those proportionalities together, come up with a statement that we think is going to be the formula. And all I've done is said, okay, from our work, we think that the formula for acceleration is going to be KR over T squared. Now, mathematically, we're going to try to come up with that number and prove it. Okay, so speed and period. In one complete revolution, the distance traveled is the circumference. Is that true or false? True. Okay, so the d distance is the circumference, which we have already established in earlier grades as equal to 2 pi r. Circumference of a circle is 2 pi r. Right? And the period is the time it takes to go all the way around. So this is our displacement, 2 pi r. Right? And the period is t. So given this, we're going to write the formula for the speed of the object, and we're going to substitute. So v equals d over t. That's a good question, Nate. Traditionally, t is the capital when we talk about period, like a single revolution. T, a lowercase t, is just sort of whatever time has elapsed. Yeah, good question. So v is equal to d over t in the general sense. So in this case here, the velocity of the circumference divided by the period, or 2 pi r over t. I've taken my really old v equals d over t formula, and I've made it into a circular sort of thing. And I get 2 pi r over t, and then I'm going to switch the t and the v, just switch them, and I'm going to get t equals 2 pi r over v. Right there. 2 pi r over v. And I'm going to say, keep this formula in mind. I'm not expecting you to memorize it, but just we're going to denote this. We're going to call this saved equation number 1. Equation number 1. Do you remember when we did the formula derivations in kinematics and we had 2 or 3 equations and we put them together, right? So we're gonna call this equation number 1 for now. Again, Nate, this is one of those days where it's going to make sense once we get to the end. Okay? When I get to the end, I'll go back and I'll remind you of the steps, and you'll go, oh, okay, yeah, right. Okay? So you're not really going to get it until we get to the end. It's kind of like watching Lost. And I still don't get it, and I've seen the finale. Yeah, that's how we felt when we were done. It was like such a letdown. I watched it live, like week by week. Yeah. Okay. Centripetal acceleration. Given the formula for acceleration, which is a equals delta v over delta t. I'm going to rearrange that to delta v is equal to a times t. Everyone here should be good with that. Okay? For one entire revolution, the delta t, the change in time, is known as capital T, the period, and the delta v, the change in velocity, I'm going to call it delta vt, total change in velocity. I'm just sort of making a little bit of a substitution there. Okay? So in other words, delta vt, total change in velocity, is equal to acceleration multiplied by period, at. Again, I'm sort of laying the foundations here. I'm creating these formulas. You don't know where they're going. I get that. I'm going to put it all together at the end. I'm going to call this saved equation number 2. No. No, don't. Again, Nate, don't worry. It's going to make more sense once you get back and you look back on it. Okay? So this is called saved equation number 2. Delta Vt is equal to A times T. Guys all good out there? You can hear me? You can see me? No technical difficulties? Okay, good. Okay, my least favorite slide in grade 12 physics trying to explain something. Really wish I had sat down and thought about it last night. I'm going to wing it. Another way to think about, and again, if you don't get it, that's fine. Just think of this as like lifting extra weights one day, right? You're pushing your brain here. Another way to think about delta V for a whole revolution. Suppose several instantaneous velocities are recorded. This is shown as the tangent lines below. So in other words, can you guys see them red there? They're red on my screen here, right? Okay, so the black ones here, which I'm going to go over in blue, that's the velocity at that point, tangent to the circle. This is the velocity here, v2 at that point right there. This is the velocity at that point. And that's true all the way around the circle, right? The velocity at every point is tangent to the circle. Each vector, v1, v2, v3, is the same length. How come? Same speed, not velocity because it's directional. Same speed. Okay? The value delta v is the difference between v1 and v2 and so on. Okay? So this red one here is the difference between those two. Okay? This delta v1 here is the change in those two. And if we place v1 to v8 all tail to tail, this is another way to show vector subtraction. I haven't really talked a whole lot about how vector subtraction is tail to tail, but if you were to take all those vectors and place them tail to tail, it would look like this black thing right here. And remember, do they only exist like at 12 o'clock and like 10 o'clock and 9 o'clock and so on? No, they exist at every point along the circle, right? So really, I could have like an entire black circle of vectors, right? I just choose not to. So if we place v1 to v8 all tail to tail, this is another way to show vector subtraction. In this fashion then, the delta v1, delta v2, etc., form a circular pattern. Okay, so in other words, these red ones here, this is delta v1, delta v2, delta v3, delta v4, and so on. And again, if I've got all these 1,000 black ones, like right now, it's sort of circular, but it's not because they're straight lines. But if the black lines are just really close to one another, then this red thing actually becomes an actual circle in that sort of calculus, taking it to the limit kind of thinking, kind of thing. I get it. Or I don't. Sometimes I don't even get it. I'm doing the talking up here. I know. So the total change in velocity is then delta Vt is delta V1 plus delta V2 plus delta V3. And because I can think about all those black ones and this red, I guess it's an octagon becoming a circle, if I talk about enough of them, delta V1 plus delta V2 and so on is actually the circumference of the red circle. And the circumference of the red circle is 2 pi r, where r is that distance there, which was the velocities, which were all the same. Hang on, I'm on a roll here. Bill says you look good today. With my disapproving frown? Very disappointed in him. Is he milking? Okay. So the radius is V1 or V2 and so on. So in other words, I'm taking this and I get that delta VT, total change in velocity, delta VT is equal to 2 pi V. Whew. And I honestly, you guys, I get that this is like crazy talk. I've taught it 25 times, and it's only been in the last few years that I really started to really understand it myself. Okay? So again, it's the experience sitting through this. No. So I have 3, because when you come back, you're going to go, I don't get it, Mr.
I don't get it either way.
Well, that's true, but no. Please hang on, Nate. Do you really need to go, or is this just I need to go for a walk? Okay, Nat, no. Sit tight, man. Delta VT is equal to 2 pi V. So now I have 3 saved equations. Now comes the good part where I'm going to start putting them back together. Bear with me. Remember equations 2 and 3. We just wrote them down. They are delta VT is equal to AT, and delta VT is equal to 2 pi V. So I'm going to, because they're both equal to delta VT, I'm going to say AT here, whoops, AT here is equal to 2 pi V here. I'm going to set them equal to each other. And that tells me I divide both sides by t, and I get A equals 2 pi V over t, and I'm going to call this equation number 4. Okay, so I've combined 2 and 3, and I now have an equation for equation number 4, and we're getting really close. Okay, Mitch and Cole, come on. You've done really well. I'm really close to the end here. I know it's hard. I just read an article the other day about kids and how hard it is for them to focus, for stretching your abilities here. Hang with me. Okay. So remembering that t is equal to 2 pi r over v, that's equation number 1. I'm going to substitute equation number 1 into equation number 4 for t. I'm going to take this right here, and I'm going to put it in there for t. And what am I going to get? I'm going to get 2 pi v over 2 pi r over v. Will there be some canceling going on? It feels like there should, right? We got this 2 pi thing going on here. Feels like there should be. So I'm going to take this here, and I'm going to plug it in for t there. I just see some people writing, so I'm pausing here. They were ones that we did earlier today, Nate. This was 2, I think. This was 3. They're the ones that I just came up with. Right? So I combine them together, and then I substitute equation number 1 in to get, I'm going to come up with, I'm thinking I'm going to call it equation number 5. What am I going to get? Oh, now you're going to start?
No, I started before.
No, you only need the one at the end. I'm going on. Going on. It's about the experience. I'm going to lose people's focus here. Okay, so I'm showing it again. What I just did. I'm taking 2 pi r over v, and I'm substituting in for t, and I get 2 pi v over 2 pi r over v. And I'm going to pull my blind thing down here. Yeah. That's what I've been saying all along, man. Yes! Have you... I wish you would just listen sometimes. I can't find my... I usually like that shade thing. Okay. So, 2 pi v over 2 pi r over v. Can I do any canceling here? 2's and the pi's go away. And I get v over r over v. The v goes to the top, and you get... There it is there. A equals v squared over r. Now, some people like it another way, which I'm going to show you. So when I take this t, Nate, when I take this value for t and I plug it in here, I can write this as 2 pi over t times v. This thing here, I can just pull the v out to the side. See it there? 2 pi over t, and then pull the v out, and you get this, right? And then I'm going to take that V and I'm going to replace it with 2 pi r over t from before. And I get multiply across 2 pi times 2 pi. There's no canceling. You get A equals 4 pi squared r over t squared, which is the craziest formula you've ever seen, I'm sure. 4 pi squared r over t squared. These two are equivalent. Yeah, well, because they're both equal to centripetal acceleration. So the centripetal acceleration is either equal to the velocity squared divided by the radius, or it's equal to 4 pi squared r over t squared. Now, v is velocity, must be meters per second. R is a radius of the circle, must be meters. A is the centripetal acceleration, must be meters per second squared, and the period must be in seconds. Now, way back about 15 minutes ago, we came up with a k. And I said we need to know what the number is for k. Do you remember what the rest of that formula was? Something, 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 right? No. What was our predicted formula based on the experiment? It was, we said, based on the relationships from the graphs, we said that AC was equal to KR over T squared. We just derived AC is equal to 4 pi squared R over T squared. So what does that tell you? What is our value of K? What is it? 4 pi squared. Are you surprised that pi is in the constant? Not really. It's a circular motion thing, right? So the value for K is 4 pi squared. Now, of course, every kid wants to know, okay, what do I really need to know, Mr. Ben? Like, give it to me, the bottom line here. What do you need to know? You need to be able to use this formula. You need to be able to use this formula. I don't expect you to do all the derivations. I'm just showing you where they come from. They don't just come from, like, the store. Like food kind of thing, right? In a sense. Do we do it for everyone? No. But, yeah, and again, it's about the experience. You're going to see way more of that as you take post-secondary science. So one of the goals for me is to give you that experience on a relatively low stress sort of environment. Okay, so we have our two formulas for centripetal acceleration. Now, I got one more thing. Okay, this is relative. It looks complicated, but it's relatively easy. Hang with me here. I'm not even going to do sample questions today. I'm going to leave those till tomorrow. So hang in here. I got about 5 more minutes, Nate. Nate, 5 more minutes. So, given our two formulas now that you need to know, these guys here, if we want a formula for centripetal force, and quite often we do, since F equals ma, yeah, and centripetal force is equal to m times centripetal acceleration. So all we do is we add m to the formulas, right? Take this value here and plug it into there, and take that value there and plug it into there. And so you get, instead of, right, if you want it to be force, you just put an m in there. If you want this one to be force, you just put an m in there. And so you get Fc is equal to mv squared over r. And the big daddy, Fc is m4 pi squared r over t squared. These are the only ones you need, Nate. Those two and these two. Oh, what's going on? Yeah. Those 4. And you'll notice that AC v squared over r is the same as mv squared over r, right? mv squared over r and m4 pi squared r over t squared. Big R is the radius. It's also what the pirate says. Yeah, actually, it can be R2. Yeah, and actually, that's a good point. Here it is in a lowercase, right? For some reason, the R flips between lowercase and uppercase. There is no intended difference. Okay. I will. I have to say this because I'll forget. I will caution you because people are so used to area is pi r squared, is I've seen kids write this as m4 pi r squared over t squared, and that is not true. It's the pi that's squared, not the r. Okay, and it's because of this pi r squared thing. So just make a note. Make sure you get that right. It's m4 pi squared r over t squared. Nate, you had a question.
What are the definitions for like for each like centrifugal FC is
So FC is centripetal force.
T squared is
Period squared. Time. T is time, measured in seconds. M is the mass in kilograms.
So period time. That's the T squared.
Yeah, T is time, period.
I'm trying to know definitions.
Okay. You mean like what those letters stand for? Yeah.
Wait a second here. No, it's there. It's you. We know.
I had a sweater like that in high school.
Oh my god.
It was the 80s.
What are you wearing with your rain shoes?
I had a computer.
I saw a picture of you being basketball coach. There. You go. It was funny. I was like, oh my god.
You mean you thought I've always been hair challenged? I was born bald, Nate.
So was I. So this still had a keeper.
Oh yeah. Someday, man, someday.
Big stillness. My grandpa was bald when he was like.
Oh, then you're in trouble, man.
No, my dad, he has lots of hair. He's like,
Apparently, it's the mother's side.
what if it skips generation?
I don't know. I know I had no chance. Both my grandfathers are bald. My brother's done well, though.
So AC is
Centripetal acceleration. Okay, so like I said, I am not going to. Usually, I jump right into some sample questions, but given that it's Friday, given that I'm missing a couple people, given that some people still owe me labs from Momentum, some people still owe me circular motion labs, graphs, I'm going to give you some time to complete that. So if you've got your Momentum lab in, if you've got your UCM lab in, you're good to go. Some of you got some work to do. Are you going to do it? No, I don't think so. I don't think it's useful, Nate.
You gonna give me a stroke for it?
No, I'm